So now we take a look at doing calculus with polar coordinates. Okay, so the first thing I'll mention is that if you have r as a function of theta and the question is to find dr d theta, we do that in the absolute standard way. In that case, you can treat r and theta just basically as any two variables, and the fact that you're using them as coordinates, that doesn't really matter. So that is basically first semester of calculus material. So that sort of thing we know how to do. We're going to look at more interesting questions. So for example, suppose you want to find the slope of a tangent line. All right. So if you want to find the slope of a tangent line, we basically need to find, we know the slope is like rise over run, it's dy dx, but everything's written in r and theta. So the way that we're going to answer this question is to borrow an approach from parametric equations. Now in parametric equations, we always thought of our parameter as t, but here we're going to think of our parameter as being theta. So we know that from parametric equations, dy dx is just dy d theta over dx d theta. And that's going to allow us to find the slope of the tangent line. And I'll just mention that it's possible but not necessary if you wanted to get a formula for the slope of the tangent line still in r and theta. So how would that look? So notice that dy d theta is just d theta of y, but keeping it in terms of r and theta, y is just sine theta. And then the denominator would be d theta of x, which is just the d theta of r cosine theta. And then you just have to calculate that out and simplify, and it looks like this. So in the numerator, you get, using the product rule, dr d theta times sine theta plus r times cos theta. And then in the denominator, dr d theta times cos theta minus r sine theta. And it turns out, okay. So for example, we can answer a question like this. If r equals 1 minus cos theta, first of all, sketch the graph, and then find the horizontal and vertical tangents. Okay. Now, for graph sketching, we could try to do it from scratch, but I'm going to use this handy chart. So r equals 1 minus cos theta. Where does that come on my chart? Okay. So that is going to be 1 minus cos theta is going to be one of these fellows up here. It's going to be a limicon, but in particular, it's going to be since a over b, the ratio of the coefficients is 1, it's going to be a cardioid. So it's going to be this graph over here. So it's going to have that little corner right in the middle there. Okay. And then also because of the signs, what you'll wind up with is basically this kidney bean looking thing right here. Okay, so that's what the graph winds up looking like. Cardioid with a equals b equals 1, with the minus sign in the middle. Okay, so that's what the graph looks like. Next, let's find the horizontal and vertical tangents. So to do that, we need, on the one case, the slope to be 0, in the other case, the slope to, for a vertical tangent, we're going to have a 0 in the denominator for the slope. So what is the slope? The slope is dy dx, which, using our parametric equation technique, is dy d theta over dx d theta. So notice that y is r sine theta, but we know what r is. R is 1 minus cos theta. So it's r sine theta. And then x is r cos theta. But again, we know what r is in terms of theta. And so this is the calculation. You just have to do this calculation. So let's work it out. Let's see. A couple ways to do this. I'm deciding to use the product rule. So by the product rule, by the product rule, it gives you this. Okay. And now we just got to do a bit of algebra there. So horizontal tangent. Horizontal tangent, we need the numerator to be 0. So you get sine squared theta plus a cos theta minus a cos squared theta. That's your numerator, and that's got to be 0. Okay. So how can we solve this out? We're going to do a bit of tricky calculation here involving both trig and algebra together. So notice that we've got sines and cosines. That's hard to solve, but we can rewrite it all in terms of cosines by converting that sine squared. So now we have minus 2 cos squared theta plus cos theta plus 1. And notice that this equation is quadratic in cosine theta. So we can use the quadratic formula just to solve that. So negative b plus the minus square root of b squared minus 4ac over 2a cranks out the answer directly. And remember that cosine theta you're treating as your variable. So so then you get 1 squared is just 1 minus 4 times negative 2 times 1 all over negative 4. And if you work that out, negative 1 over negative 4 is just going to be 1/4. And then you've got 1 plus 8. So that all is going to be square root of 9, so that's 3. So you get 1/4 plus or minus 3 over, it's negative 4, but that negative, it's a plus minus anyway, so it's okay. So this means that cosine theta, if you do the plus, you get 1. If you do the minus, you get negative 1/2. So when does this work? Well, cosine theta is going to be 1 when theta equals 0. And then cosine of theta is going to be negative 1/2 when, okay, so we use our reference angles here. So it's going to, the reference angle is pi over 3, but we want it in the second and third quadrants. 2 pi over 3, 4 pi over 3. So that tells us when we're going to be at our horizontal tangents. What about the vertical tangents? So for the vertical tangent, oops, sorry about that. Vertical tangent is going to be a very similar looking calculation. 0 equals the denominator. Sine theta, cosine theta. Then you get a minus sine theta. Then you get a plus sine theta cos theta. This we can actually factor out. We can combine, we get 2 sine theta cos theta, and then we can factor out a sine theta. So sine theta, 2 cos theta minus 1. Okay. So this tells us that sine theta equals 0, or 2 cos theta minus 1 equals 0. So sine theta equals 0 gives us that theta equals 0 or pi. And then over here we get cosine theta equals 1/2. And again, we got to check our reference angles. Over here, you get theta is going to wind up being first and fourth quadrant, pi over 3, or 5 pi over 3. So that tells us at which theta values we're going to find our horizontal and vertical tangents. And then finally, we can confirm this by looking at the graph. Looking at the graph, where do we have our horizontal tangents? So there's one on top, there's one on the bottom, and then there's also going to be, I didn't draw the cusp very well, but it actually comes in kind of flat at the origin. So there's going to be another one basically at the origin. Okay, so that's the first thing. It's a cusp, so it looks a little weird. So that's the first bit. Second bit, where is the vertical tangent? So we're also getting something going on at theta equals 0. So what's happening is that we've actually got the numerator and denominator equal to 0 when theta equals 0. It's a cusp, so we'd actually have to do a little more work calculus-wise to figure out precisely what's going on there. Graph lets us know that that there's a cusp there, so it's a complicated spot. Okay, so let's just focus on the sort of more traditional points. As far as vertical tangents go, looking at the graph, you can see there's one on the left and 2 on the right. There's going to be one over here and one over here, and then on the left, another one over here. And notice how that corresponds to, on the left, we've got theta equal pi, and on the right, we've got something in the first quadrant and fourth quadrant, and as it turns out, we found the angles for that. So that was a bit of a long and tricky one as far as doing the calculations, but that's the basic idea. That's how that goes. So as far as polar coordinates go, that is how we use derivatives to find out certain things. In this case, we're trying to find dy dx, the slope of the tangent line. That's the first bit. Second bit, calculating the integral. Now, once again, if we just have an expression, r equals a function of theta, so some expression in theta, and we're just integrating it d theta, then that is just standard single variable calculus stuff. We know how to do that. You can ignore the fact that they're polar coordinates. So we're going to ask a trickier question. What if we want to calculate area using polar coordinates? Turns out this is actually a bit harder than it might first appear. Let's take a look why. Okay. So notice that x times y is an area, or you can think of this little delta x times delta y is an area. However, r times theta is not the same thing. So we need a new formula. We're going to take a familiar approach, and we're going to try to add up small areas. In polar coordinates, what's the basic unit for which we know the area? So polar coordinates define circles, or r defines a circle, but if we use r and theta together, it's going to give us a slice up high, and that's called a sector. So note that the area of a circle is pi r squared. So the area of a circle will be whatever fraction of the circle that is. So that times theta over 2 pi. Pi's cancel, you just get 1/2 theta r squared. So if we assume that r is a function of theta, which is what we're going to do for these cases for now, then we can say that in a small slice, the quote-unquote width is delta theta and the quote-unquote height is r. So therefore, the area of a small slice, which we can call our delta A, is going to be 1/2 r squared delta theta. And of course, if we want the area of all slices put together, approximately just add up all the delta A's. That's 1/2 r squared delta theta, sum over that. But of course, we want to make this exact. And when we make it exact, sums become integrals, deltas become d's. So the area is exactly the integral of dA, which is the integral of 1/2 r squared d theta. So notice how this definitely does not look like what we would do if we were working in rectangular xy coordinates. So let's use this formula in order to do a problem. Okay. So find the area enclosed by a limicon, and the formula for that is r equals 2 plus cos theta. Okay. So I just want to make sure that we know really clearly that a limicon is like a loop. So let's take a real quick picture. So this is a limicon where the ratio, so it's 2 plus cosine theta. So we're in the top right picture here. It's a convex limicon. The point is that the enclosed area, we have to go once all the way around, kind of like a circle. So the boundaries of integration must be 0 to 2 pi. Now you can also see that just by noting that r plus cosine, 2 plus cosine theta, it never equals itself until theta wraps back around, because we never have 2 equal to cosine theta. So okay, so we know that the area A is just going to be the integral of dA, which is the integral of 1/2 r squared d theta in general. And what is it in this case? Well, we've got the 1/2, and we know what r is. It's 2 plus cosine theta, and we've got a d theta, and then the boundaries, as we just discussed, are 0 to 2 pi. And now we've got this integral, we just have to go ahead and do it. So I'm going to take the 1/2, I'm going to pull it outside. And I'm just going to expand. Oh, sorry, that was squared. Okay, so 2 plus cosine theta squared. Sorry, so now I have to square it out. So 4 plus 4 cosine theta plus cosine squared theta, all that d theta. And to integrate this, the first two terms are okay, but for the third term, we need to use the double angle formula. Four plus cosine theta plus is going to be 1/2 plus 1/2 cosine 2 theta, all of that d theta. Sorry, okay. And so we keep going. Yeah, so now we just integrate. So now I'm just going to combine 4 plus 1/2, so that's 9/2. So the integral of 9/2 is 9/2 theta. Integral of 4 cos theta is going to be 4 sine theta. And then the integral of 1/2 cos 2 theta is going to be sine of 2 theta. But after doing the substitution, another 1/2 is going to pop out. So we're going to get 1/4 sine, sine of 2 theta. And all of this evaluated from 0 to 2 pi. Now notice that sine of theta plugging in 2 pi and 0 is going to give us the same thing, so that's going to cancel. Sine of 2 theta is going to give us sine of 4 pi and sine of 0. That's going to be the same thing. That's going to cancel. So long story short, long story short, the only non-zero thing we're going to get is 1/2 times 9/2 times 2 pi. And that's just 9/2 pi. So that is how we can calculate area using polar coordinates. More things that we can do with integrating with polar coordinates. We can figure out length. So we're going to start with the classic arc length formula, and once again we're going to use our parametric equation techniques. So now, so remember the old arc length formula, which is the integral of the square root of dx dt squared plus dy dt squared, all that dt. Only instead of t, we just use theta. So in other words, arc length is just going to be the integral of the square root of dx d theta squared plus dy d theta squared, and then all that d theta. So you can leave it like this, or we can rewrite it completely in r and theta. So if you do that, after a bunch of lengthy calculate, so dx d theta, we calculated previously in an earlier problem, and that was just dr d theta cos theta minus r sine theta. Dy d theta, we calculated previously, it was dr d theta sine theta plus r cos theta. And again, you can just use the product rule to work it out. Now, if you square it out, you get this whole mess. Now, if you really want, we can actually simplify this. We can do a whole bunch of algebra and trig identities and simplify this into a nice formula. Yes, it actually simplifies to this. The formula for arc length in polar coordinates is just the integral of the square root of dr d theta squared plus r squared, all of that d theta. So for a circle radius 3, let's find the circumference. So that's just an arc length. So it's the integral, and again, this is a circle, so obviously we want, well, first let's set up the basic formula. Dr d theta squared plus r squared, square root of all that, d theta. And now for this particular problem, we know the boundaries because it's a circle and circumference. We know we're going 0 to 2 pi. And then dr d theta, notice that r is just 3, so dr d theta is just going to be 0. And then plus r squared, r is just 3, so that's just 3 squared, square root of all that, d theta. Well, that's just the integral of 3 d theta from 0 to 2 pi. That's just 3 theta from 0 to 2 pi. And that's just 6 pi. Also notice that this tells us the general formula for the circumference. We've actually proved it. If instead of 3, we write r for the radius, the circumference is going to be the radius times 2 pi, or 2 pi times the radius, so 2 pi r. And there you go. Okay. We can do a slightly trickier one. It looks like this. So find the length of the cardioid, which has the formula r equals 2 minus 2 cos theta, as theta goes from 0 to 2 pi. And this is a setup do not solve. Length equals d theta squared plus r squared, root of all that, integral of that d theta. So that's just the integral from 0 to 2 pi. So dr d theta is gonna be 2 sine theta squared, and then plus r squared, so 2 minus 2 cosine theta, that business squared, square root of all that, d theta. And we're just going to set up and not solve. And again, you can figure out the boundaries because the graph is given and you can see that going, you need to go once around. Yeah, although the boundaries are also given. Okay. And then from here, this, if memory serves, this is not an integral that you can do by hand. So you could just punch this into some solve. Okay. And we bring in yet another application from single variable integration, calculating the surface area, but with polar coordinates. So we know the old formula was to find the surface area. We thought of it as 2 pi h times the length. So that wound up being 2 pi the integral y square root of 1 plus dy dx squared dx. We can now update that by simply using what we know our formulas are. So we know that we have our new arc length formula that replaces the last part. We have a new formula for y in polar coordinates, that's r sine theta. So we can either write it in the first form, just using the parametric technique. So 2 pi integral y square root of dx d theta squared plus dy d theta squared d theta. Or we can use the simplified version that we just showed, and that's going to be 2 pi integral r sine theta, and then the square root we know reduces to r squared plus dr d theta squared, and then all of that d theta. And then as a side note, to rotate around the y-axis, which is now the theta equals pi over 2 line, note that your height is going to be x instead of y. So here is a sample calculation of something kind of cool. The surface area of a donut with no hole. Previously we saw r equals cos theta gives us a circle on the right side. Now we're going to take that and revolve it around the vertical axis. So that's going to be So first you have to note that theta goes from 0 to pi, gets you once around. Forms the entire circle. So those are our boundaries of integration. Secondly, now we just use the formula. So it's 2 pi on the outside as a constant. We can take down the outside. Now, r cos theta. So notice that r just equals cos theta. So plug that in, and then times cos theta, and then times the square root of. And now we use the simplified version. So r squared, that's just cos squared, plus dr d theta squared. Dr d theta is negative sine squared. So we square that and just get sine squared. And now we can simplify square root of cos squared plus sine squared. All that's just 1. So you're just integrating cosine squared theta d theta. To do that, we use the double angle formula. And so we get 1 plus cos 2 theta. And notice that the 1/2 cancels with the 2 in front. And that we can integrate pretty straightforwardly. We get theta plus sine 2 theta over 2 with the constant pi in front. And now we just evaluate from 0 to pi, plug it in, and you get pi squared. So this object, which is called a pinch torus, there's your surface area.